Hello friends, hi everyone. My name is Vladimir Arifman. Welcome to my channel. We are already in the fourth lesson on developing smart contracts using the Tact language. In this lesson, we are going to see the first differences that the Tone blockchain apart from other blockchains. We will get acquainted with details of how contracts interact with each other, how they send messages to each other, and about the asynchronous nature of the blockchain. This future leads to a different approach in development, so sit back comfortably and let's get started.
First of all, let's recap what we already know. Specifically, to process messages in a smart contract, the receive method is used. And then the message we want our smart contract to process is passed on. We can also choose not to pass any message to the receive method. That means that our smart contract is able to receive Tone coins without any conditions. However, if we didn't have such a method and we simply send Tone coins to our smart contract, the transaction would not go through. It would be rejected and the Tone coins would be returned to our wallet. Here I have prepared a few messages that our smart contract works with. These are the add message for adding an amount to the total value, a similar message for subtraction, and the message for setting several operations that we want to execute in the contract at once. As we remember, messages can also be textual. In fact, textual messages are much more convenient for the end user because user can see exactly what they are confirming in their wallets. However, in the case of message type, we have embedded several fields of different types, and for the users they will be presented in the form of a binary message and they won't be readable. But they are capable of accepting several arguments, unlike textual messages. Although in the future we are promised support for both textual messages and the ability to pass arguments through them, so that the user can be both what they are signing and what arguments are being passed. Also, in the receive method, it is possible to pass a string type message. We will end up here if we send a textual message to the smart contract and it did not match any other textual message that was defined in the smart contract. Therefore, if we had sent textual nonsense to our smart contract, we would have ended up in this part of the code. A similar example is below with the slice type. A slice is a somewhat low-level data type. It means an open cell, and in the slice unprocessed data are stored. Unprocessed means you can put an address, strings, number, and anything that can be exist in the Tone blockchain into it. If we had passed a message that was not only by value, but also by type, we would have ended up in this part of the code. Speaking of messages, I think it's worth noting the structured data type in Tact. Structures look exactly like messages. Furthermore, they can be used as message bodies. The difference between structures and messages is the way they work under the hood. When compiling code in Tact, each message creates a unique identifier under itself, which the smart contract uses to determine what logic to execute when receiving a particular message. Structures do not have this identifier, which is why they cannot be used in the same way as messages. Alright, I think it's time for us to understand how smart contracts interact with each other through messages. For this, we will create our favorite smart contract, counter. I will use a pre-made template to make it faster. Okay, and I'll modify it a bit. I won't be using the query ID here. Also, my increment will be text only. And that's it. We have our get counter. Excellent. Now I am going to write another smart contract that will interact with the counter contract. Its goal will be to increase the counter to the value which will be specified in the logic of this contract. To achieve this, we will have to read the storage of contract counter and send a message to it, a message increment. It might sound unclear for now, so let's start writing it, and I'm creating a new smart contract. Okay, in this smart contract, I'll have a variable called target of the integer type. Upon creating of the smart contract, target will be set to 0. The first thing I want to do is for this smart contract to be able to send messages to the counter smart contract and read its storage, read its counter value. To begin with, we need to add a new receive to our counter, and it will be a textual message query. Next, using the add message, I'm not very like for this name, so let me rename it to counter value. It will be better reflect what we are doing. So upon receiving the query message, our smart contract will send back the counter value message. The value of amount will be the counter. Let's try to make this happen. To send the message back to the sender, the default method self-reply is used, and the body of the message is passed inside. We form it in the following way. We write the type counter value, then the amount field, and as a value we used self counter. We convert all of this into a cell. Okay, our contract is ready to receive messages from another contract and return to it a message with its own storage. Now let's recap once again the purpose of the second smart contract. Its goal is to send increment messages until the counter don't equal to target variable. Currently it's 0, but we will modify it. First, as we as users will be sending these messages to this smart contract, we need to format this message. In this case, it will be a rich message, which means what we want to achieve. We will pass the counter field, which in this case will be the address of our counter smart contract, and the target field. All we will do is send one message to the contract. And the first thing we do here is initializing the target variable and then formulating the transaction which we will send to the counter contract. The send method, then send parameters, and we list the parameters. The first is to, where we pass the recipient's message address. For us it's counter. Value is the amount of ton coins we want to send, which is 0. We will talk about the mode field in the next lesson. For now, I just fill out the fields as needed. And in body we pass the body of our message. In our case, we will send the first request, query. We need to know the current counter in our contract. Okay, and we can note here that this is our first step. Then, after the smart contract sends this message, our counter contract will receive it. This will be step 2. At step 2, it will send a new message, it will reply, and counter value will be used at the body of the message. This means that step 3 for us will be to accept this message. For this, we need this message interface in our contract. Let's add it and receive it now. The first thing I need to do here is to check if my self-target, I guess it will be 5 in our test, if my self-target is more than counter in another smart contract. We use the if operator and specify that if self-target is greater than message amount. Then the next logic is executed. Specifically at this step we will send an increment message. Here, to initialize the field 2, we can use the sender method, because at this moment the sender will be the smart contract itself. And we specify the increment message as the body. Great, so we are moving to this part of the code, and this is already step number 4. Having received the increment message, we increase the counter by 1. At this point, all our operations at this location will end, because our contract doesn't send messages anywhere else after this. This doesn't suit us because our goal will not be achieved. Our goal is that if target in this contract is 5, we should send increment messages until counter also becomes 5. This means that in this part we should send a message to our first smart contract again. Okay, we are done now. Let's try to write a test for it, but first let's see if our smart contract will compile. There is some error here. Yes, I forgot the semicolon here. And here too, you need to put a semicolon. So the first smart contract is compiled. Now let's compile the counter contract. Yes, it's compiled successfully at the first attempt. Great, now we go to the tests. I will only need one test, so I will delete the rest. Okay, in this test I will be working with 2 contracts. I will also duplicate the deploy counter next to the first contract. Duplicate deploy, and I will also move deployers to a higher scope. Okay, let's check that our smart contracts will deploy first. The deployment was successful, and our test will be called should increase to target. And here we will only send our reach message to our smart contract. There are 2 fields that we need to pass here. The first field is counter, which takes an address, and the address will be located here. And also target, which takes a number. Let's first try to pass target as 1. Okay, TypeScript complains about it here. Let's fix it. Good. And we will get the counter here. We expect the counter to be equal to 1. In general, let's do it a bit more beautiful and bring target out into a separate variable. Okay, let's run our test, and at the same time I want to show you what will be happening under the hood. What messages will be sent in the blockchain. For this, I will display the result of this operation in the console. So for starters, all our tests have passed. And now let's look at the console, and here we will see several messages. We can start breaking them down. In fact, little will be clear here, but the most important thing for us is to see the quantity, the number of these messages. And here we have them. Let's count it, and I see 1, 2, 3, 4, 5. Yes, that's right, which means if we go back to our contract code, we will see that we had 4 steps in total, and here you need to take into account the step that was sent from our wallet, message reach. So in total there were exactly 5 messages. And now let's see what will happen if we increase our target to at least 5. How many messages will appear here? And we see that everything went successfully. We have 13 messages here. By the way, it's important to understand that if, for example, I set a value of 30 in target, then probably we will now get an error, because you also need to take into account how much gas will be needed to these messages or be executed. We already see the error. This is due to the fact that the more our smart contract interact with each other, sending each other messages, the more gas fees need to be paid, and at the moment our 0.2 toncoins was not enough for all messages to be executed, and our expected counter was equal to 30, but gas was enough only for 11 full cycles. Let's increase the number of toncoin here to 6, for example, and we see that the number of events has already reached 63. Okay, we have covered the interaction of smart contracts with each other. Now let's look at how to deal with smart contract errors. Sometimes we don't want to allow certain actions in smart contracts, and for this we need to intentionally throw an exception, intentionally throw errors to prevent what we don't want. The first uses the keyword require, and such a line of code will throw an error, an exception. There are two ways to do this. The first uses the keyword require, and such a line of code will throw an error, an exception, if this expression is false. If it is false, we will get an error with such content. Let's try to make sure of this. And yes, we really got an error, because all our operation stopped at the very beginning when we stated that our target will be more than 10. Let's take closer to look at the logs. We didn't get to them, so I will put them a little higher. Great. And here we see two messages. The first message is from our wallet deployer to the smart contract address, and what I want to show you here is such a field as bounce message. As we can see, the first message has a bounce value of false, and the second message has a bounce value of true. Bounce true indicates that this message is a bounce, meaning it bounced back due to some error. Therefore, it bounced specifically because of an error, and this is the first way errors can be thrown in smart contracts. The second method will look as follows, using the throw method. Here, if we enter this block, an error will be thrown, and we can pass some error code in the body. But the most interesting part here is that errors in tone are also considered messages, and they also convey information. If errors are treated as messages, they can be handled in the same way as other messages. And to handle a message that carries an error, a similar approach is used, but instead of the receive method, the bounced method is used, where the message body is also passed. I will create two additional smart contracts to better understand how to handle error messages. I will create two smart contracts that will interact with each other. The first smart contract will act as a fund, while the second contract will represent a company. Let's start by writing the fund contract. It will be very simple. We will have a single storage field, which is the balance with the integer type. By default, let's set our balance to 10. Additionally, we will specify that our smart contract cannot accept ton coins, but it can receive deposits through messages to update the balance in our storage. We will also implement the functionality to withdraw this balance. The withdrawal of the balance will work as follows. First, we check if our current balance is greater than or equal to the amount we want to withdraw. If it is, we decrease our balance and send a message to the company. We are almost done with the fund contract. Let's write a company contract. In fact, it will be very similar. We will also have a balance field here. Our balance will be set to 0 by default, and we will also implement the functionality to receive deposits. Let's build our contracts. After that, we will write a simple test to verify the current logic. I might have missed some semicolons, but we can fix them easily. There is a typo here. Great, the contracts have been compiled successfully. Now let's write the first test for them. First, we'll check to see if our contracts have been successfully deployed. Next, we will revise the previous test, ensure everything passed here, and remove the console logs. Let's take another look. First, we will check to see if our contracts have been successfully deployed. Next, we will revise the previous tests, ensure everything passed here, and remove the console logs. Let's take another look. The contracts have been successfully deployed in the background. Now I'm going to write just one test for the withdraw method. After this transaction, I'll extract the balance of the fund and the balance of the company. For some reason, getBalance doesn't exist in the company. Let's try now. All good. We expect the balance of our fund to be 7 and the balance of the company to be 3. Great. All our tests have passed successfully. But let's consider what will happen if an error occurs during the withdraw method. To be precise, after the withdraw method completes its logic, then it will send a message, and since Stone is an asynchronous blockchain, this message won't be executed in one block or in one transaction. It can be executed in another block, and the success of these transactions isn't guaranteed. For example, if some error occurred in the company's smart contract, like there is an additional field type like query ID in message deposit, then the message deposit in our funds contracts won't match the message in the company's contract, and this particular receive simple won't exist in the contract. This means the message will be rejected and a bounce will happen. Let's take a look at this. First, we'll build our company's contract. Let's go to the test and see the logs. Of course, we saw an error. The console logs should naturally be higher than our checks. So I'll comment out all these checks for now. Here we'll see our log. The first message is from our wallet to the funds contract. Next, our fund sends a message to the company's contract, and the message is also being sent well. But now a message from the company's contract is bouncing back to the funds contract, and we see this through the bounce true field. Of course, we will handle this bounce in our funds contract. To do this, as I said before, we use the keyword bounced instead of receive and pass the type of the message they can bounce. In our case, this is the deposit message. All we need to do here is to restore our initial balance, because as it seemed to me I didn't show it here, if you don't do this, our funds balance will decrease and the company balance won't increase, which means the amount we are trying to withdraw will be lost. Let's try now to output this to the console. Yes, we see that our funds balance is not 10, but 7, and the company balance is 0. So 3 coins were simple lost. Now we will fix this by duplication the deposit logic in the bounce method. In this way we restored our balance. Okay, let's rebuild our fund contract again. The contract has been built, and now let's run the test again and make sure that our funds return to the value of 10. Yes, we see it.
Excellent, and congratulations, we have finished the code. We have reached the end. It was indeed an important lesson in smart contract development on Ton. We have covered an important topic, and in the next lesson we will learn not only how to send our messages, but also how to send the cryptocurrency Ton coins in these messages. And accordingly, we will look at how the Ton network fees and gas costs work here. All this will be in the next lesson. That's it for today. Thank you for your attention. Goodbye.